I'm going to present this Neur2SP 2022 paper, which we presented a couple of months ago, which is the work led by Justin and Rahul, who are PhD students at the University of Toronto, and my colleague, Professor Merve Boudour. So everything on this paper, code, slides, poster, paper are on this one consolidated link, so I invite you to check that out if you're interested. So I've traditionally worked more on machine learning for mixed integer linear programming in various flavors, and there the kind of perspective was to modify solver behavior in a way that leverages characteristics of certain instance distributions and stuff of the sort. So it was kind of inside the solver, and to that end we've developed a variety of techniques spanning supervised learning, reinforcement learning, using machine learning models that are simple, linear, multi-layer perceptrons, all the way to graph neural nets and some other custom methods. But recently I've also been looking at machine learning for discrete optimization beyond the beloved mixed integer linear programming case. The reason being that as the problems get harder in a certain sense, there might be more need for data-driven algorithms where exact methods start struggling, designing approximation algorithms becomes harder. And some of these themes are highlighted here from kind of recent works. For example, column generation, where you have exponentially many variables in a linear program. And there's a column generation procedure, and you would like to speed that up. The other cases in graph optimization, for example, recently in this transaction of machine learning research paper, we looked at an online bipartite matching problem. So you have uncertainty in the mix, so it's no longer a deterministic, nice, single-step optimization problem. But what I'm going to talk about today is the application of machine learning for stochastic programming. So there will be many themes in this talk that relate to some of the previous talks that you've listened to. For example, Pascal's talk on surrogate models, Louis Martin's talk that has a flavor of stochastic optimization, and so on. But let me define a specific context for the paper. So I'm going to use the stochastic server location problem to illustrate two-stage stochastic programming. So think of this as a kind of special case, if you will, of facility location. So the circles are potential customers, and the squares are potential locations where you can put servers or facilities that can serve those customers. And of course, there's a bunch of constraints, costs to transport from location to customer to server, and so on. We're not going to concern ourselves with exactly what these are. But the stochastic problem says that there are multiple scenarios that you could encounter. So it's not that all clients are known in advance. In scenario 1 here, only the red subset of clients is available, maybe with some probability. Okay? And if you cared only about that scenario, that's a deterministic problem, you might pick, say, this solution and ignore the bottom right solution because you can serve the customers from the 3 others. And maybe here you're minimizing some combination of fixed costs of using a server plus transportation to customers and stuff like that. Now, if you had this other scenario where a different subset of customers is to be served, you might have another scenario-wise optimal solution of location plus assignment. So which green squares do you use and which customers do you assign to the allocated green square? But if you cared about the average quality solution, right, then the optimal solution might look like something completely different. Okay, so this is, say, an optimal solution in the STOI example for the expected cost across these 2 scenarios, and it's neither the scenario 1 solution nor the scenario 2 solution. Okay, why? Because in the solution we're having to trade off between the 2 scenarios and find something that's kind of a nice middle ground. Okay, formally, you can write down a 2-stage stochastic programming problem in this form. What really matters, although we say 2-stage, what matters is the first stage decision. Okay, I'll make it clear. Here you already see that our main decision variable, first stage decisions, is this vector x. And let's say we'd like to minimize a combination of the first stage cost. Here I'm using a linear function, doesn't need to be linear, plus the expected cost over a bunch of scenarios that determine the second stage problem. So for the previous examples, this psi here is just which customers need to be served, okay? And that's a random variable. So think of it here as a vectors of zeros and ones, okay? And you'd like to minimize the expected cost of, say, serving those clients, except that depends on your first stage decision, right? So you cannot serve a customer from a location unless you've allocated that location in the first stage, okay? So you commit in the first stage, and then an uncertain random scenario gets realized, and then you need to solve the second stage problem. That's why you care only really about the first stage, okay? Now, of course, in an offline planning situation, you try to solve for the average case. You take the first stage decision, and then at test time, you observe some scenario, and then you solve the second stage problem for that scenario. Okay? That's why you care about the first stage decision. That's why you only put the X really here outside. And of course, there might be some feasible set, right? Arbitrary constraints. This can be mixed integer. You can have linear, nonlinear, whatever. Okay, this all fits under this single mode. And actually, two-stage stochastic programming finds a variety of applications. Here I mentioned some of the more classical applications in airline scheduling, power systems, unit commitment, production planning, water resources, hospital staffing, and so on. So essentially, every deterministic problem you can think about has a two-stage stochastic variant where there's uncertainty about demand, about capacity, about price, about cost of certain materials, and so on and so forth. Okay? So the two in two-stage models is not really that much of a special case. So two-stage planning is a common situation. And of course, there are generalization of this framework to multi-stage decision-making. But the two-stage problem is not really a small special case. It's an important, widely applicable special case. Now, what makes this problem interesting is that this value function here, so basically the optimal value of the second stage problems for a given first stage decision and scenario, this object, because it's an optimal value of an optimization problem, it might be really intractable. Okay, so the second stage problem, just computing qx psi for a known x and psi, that can be a mixed integer program on its own. Okay, and then you have on top of that the expectation. So just evaluating this is essentially intractable in general. Okay, so if evaluating this is intractable, you can imagine that optimization is even more intractable. And just to give you a sense of what this combined objective function looks like, I like this illustration from a short tutorial on the topic from Shabir Ahmed. And here what we're looking at is exactly one specific toy example of a two-dimensional problem. So x1 and x2 are your two first stage decision variables. And on the z-axis here, you have the total cost. Oops, the total cost here. And what you can see is that this objective function is quite complicated. It's you have integer variables, it's discontinuous, it's non-convex. This is actually a specific kind of two-stage stochastic program. This is the simplest one. Okay, so this is a two-stage stochastic program with linear constraints in both stages, and I think pure integer variables in the first stage. This function has a very nice structure. It's a lower semi-continuous function. You can prove stuff about it. But in general, as soon as you have continuous variables, nonlinear constraints, etc., becomes much harder to characterize the shape of this function. Okay, so very hard, thorny optimization problem. Now, this expectation is a little bit annoying. So what do people do? They use the sample average approximation method. Okay, sample average approximation. Anytime you solve a stochastic optimization problem, essentially you're doing some form of SAA. Okay, an SAA shows you that if you draw enough samples from your distribution over the uncertain parameter, and you just solve for the average of that, under some conditions you will converge to something almost optimal for the original full distribution. So we're going to be in this regime where we're going to draw samples from these distributions. The samples here are again a scenario. So in the case of the stochastic server location, these are just vectors of which customers must be serviced. Okay, and then if you do this transformation, you get something like this. So this is a figure from a famous book by Berge and Louveau on stochastic programming. So if you had, say, 3 scenarios in this case, and the value function q looked something like this for scenario 1, so here you're varying the x variable, something like this for 2, for 4, this average might look something like this. In this case, kind of a piecewise linear function, but again, in general, it may not look this nice. Okay? All clear? Any questions about just the mathematical statement of two-stage stochastic programming? Good. Okay. Now, as soon as you have a finite number of samples, because you're doing sample average approximation, you can transform the problem into a deterministic counterpart. Okay? This is known as the extensive form of the stochastic programming problem. So what you really do is you observe that now the value function is nothing but the optimal value of the second stage optimization problem. So here you have some second stage variables y, and they belong to some feasible set, which depends on the uncertain parameters. And you want to minimize an objective function, which also depends on the uncertain parameters. Okay? So that's your second stage problem. And what you can do is you essentially can fold the second stage problem, k copies of it, into one big problem. Okay? So this is what you would do. So now you take this objective function, you pull it out into the first stage objective, and you have some constraints. And here you've already sampled the capital K psi vector. So now everything is known and deterministic in some sense. Okay? If you're doing this for, say, integer linear programs, your constraint matrix, if you're representing the constraints as a bunch of coefficients, so each row is one constraint, takes this very special block structure. So the variables that are in the first block here are the first stage variables, and then every one of the k blocks is one of the second stage problems, and you have k of them. Okay? And these are essentially decoupled, except for their dependence on the first stage variable. They're all tied to the first stage variable because you fix the first stage, and then you solve the second stage as a result. But the problems themselves are kind of independent from one another. That's why you get this block structure. Okay? Now, if you can write this sample average approximation problem using this extensive form, you can pass this to a deterministic solver. Okay? This might be a mixed integer linear program if all your variables are mixed integer and constraint are linear. It might be a mixed integer nonlinear programming solver. Okay? But the main idea is you have it in deterministic form. So you've gotten around the randomness part. Except, of course, the size of the problem can become very big. So that your number of variables is number of first stage variables plus number of scenarios times number of second stage variables. And your number of constraints also depends on the number of scenarios. So if you're trying to approximate this expectation well, and you need to draw 10,000 scenarios in order to approximate a good solution for your distribution, then the size of this problem really blows up. And although integer programming solvers are generally quite efficient, quite advanced, we use them a lot, this can very easily go beyond their limits very quickly. Okay? So this is the extensive form method, which is essentially the most generic way of targeting. This is just a recipe. Any two-stage stochastic program for which you have like a analytical form for your objective and your constraints, you can write like this. Okay? And there are better approaches, but the issue is that they depend on which types of decision variables you have and which types of constraints you have. So do you have both continuous and integer variables? Are your integer variables binary or not? Are your constraints linear or not? Are they quadratic or not? And so on and so forth. So you have to specialize a lot. One example of a very famous and useful method in one particular common case is the integer L-shape method, which uses a Bender decomposition type approach when you have binary first stage and mixed integer second stage linear everywhere. Okay? These are the two main references for the method, and recently Andrea and co-authors have also incorporated a form of machine learning in this algorithm, okay? Which is very similar to what we do in Spirit, but not in how it's applied. Okay? So I'll explain that distinction later on. But essentially, this is limited to this case. Okay? So as soon as you have, say, continuous variables in the first stage, you can't really apply this algorithm at all. Okay? If you have nonlinear second stage, we'll see a problem of that form. I mean, there are no real good algorithms for these cases. You have to write 5, 10 papers to solve the problem, basically. So what is the proposition? The proposition is to use supervised learning to get rid of the main bottleneck in two-stage stochastic programming. Okay? The main bottleneck is this value function, which is the optimal value of an optimization problem. Okay? So what we're going to do is operate within the following setting. You are given a single two-stage stochastic program with a fixed cost function C for the first stage decisions, some fixed feasible set for the first stage variables, and some second stage feasible set function Y. And what's varying is the scenarios. Okay? So you have the same set of servers, right, and the same set of customers. And every once in a while, you solve a stochastic programming problem where what's varying is the scenarios that you need to account for. Okay, so maybe you solve the same planning problem, but you solve it for different days, different hours of the day. Okay, so what's changing is the scenarios that you need to consider in this expectation. Okay, but here the assumption is that everything else is fixed. Okay, that's not a huge restriction. With some deep learning magic, we can make this generalized to wider classes of problems where the number of first stage decision variables and second stage variables can vary. It's not a huge issue. We know how to get around it. It's just a matter of implementation. But for now, let's assume everything is fixed and it's the scenarios that generate data for us. Okay? And the goal is to learn this function, Q tilde, which is parameterized by some theta vector. Those are the parameters of our machine learning model that approximates the true value function. Okay? That's it. That's the main idea. And then what we're going to do is we're going to plug this approximate function as a surrogate for the true value function. Okay? Of course, this is doing nothing if Q tilde doesn't have some structure which enables efficient optimization. Right? We're just replacing a complicated object with another complicated object. So the key properties of the surrogate here is that it shouldn't be an optimization problem, okay? Because the issue with two-stage stochastic programming is you have this nested, you have an optimization problem in the objective of an optimization problem. So our surrogate should not be an optimization problem. And second, we would like that this function should be expressible as something we're familiar with, that we know how to optimize. In this case, say a mixed integer linear program. Again, it could be maybe a mixed integer nonlinear program if you have a powerful solver which you're happy with. But for now, we're going to content ourselves with a mixed integer linear program. Okay, any questions on the setup? Yes? Uh-huh. Uh-huh. So I just want it to be MILP representable. Yeah, as a function. So it's a function that you can express as a bunch of linear inequalities using mixed integer variables. Okay. So just representable as such. Okay? Yeah. Other questions on the setup? Okay, so what is the form of this class of functions we're going to consider to do this approximation? We're going to consider the very familiar multi-layer perceptron with ReLU activations. Okay? So first things first, what is this model trying to do? It takes as input a first stage decision vector, the allocation of servers in the stochastic server location problem, and a scenario vector, which customers need to be serviced. Okay? And it must predict the value of the second stage problem under that x and psi k. Okay? The parameters theta of the model must be tuned so that it's accurate on average over a large set of such input pairs. Okay? X tilde correct Q. The ReLU here is important because the ReLU is a piecewise linear function, and you can express the ReLU as a mixed integer linear program. And then the stacking of ReLUs gives you one big mixed integer linear program. Okay? Nothing magical about this, just a ReLU network is representing a piecewise linear function, and you can write piecewise linear functions as mixed integer linear programs. Okay? You could have other activations that could be representable in the same way. And again, if you needed for whatever reason a different kind of nonlinear activation function, as long as you know how to write down the overall model as a mixed integer, say, nonlinear program, that's fine. This works generically for that, okay? It just happened that we considered the most kind of obvious candidate for the task, okay? So that will be the neural network that we're going to try to learn within. But this is just kind of the backbone. So we're going to do a lot more with the overall architecture to make it work and scale well. But at a high level, the system that we're proposing, Neur2SP, operates in this way. In the learning phase, you have some two-stage stochastic program where, again, the scenarios may vary. You have a data collection phase. It's a supervised learning approach, where for that 2SP, you collect first stage decision, scenario set, and expected second stage cost triplets. This is similar to what Louis Martin called the MIP labeler, okay? The MIP labeler here is for a fixed first stage decision and scenario set, I can just run the MIP solver and get the second stage cost. And then I can say, take the average of those if I'm considering a set of scenarios. So this gives us a data set of inputs and outputs. And then we can just train a regression model that looks like the one I showed on the preceding slides, which takes as input a first stage decision and a scenario and spits out the expected second stage cost for that first stage decision and scenario pair. Okay? Once I have that model, now at deployment time, at test time, I receive a potentially novel set of scenarios that I need to consider and solve the two-stage stochastic program for. Because my neural net can be representable as a MIP, I MIPify it, meaning with its fixed parameters, I write down the linear inequalities that represent that fixed function. Okay, it's been trained already. And now instead of solving the very complicated two-stage stochastic program from earlier slides, I solve this surrogate problem. Okay, I find a first stage decision that minimizes the sum of the first stage cost plus the approximate expected second stage cost, where the approximation is coming from this trained neural network. Okay? Any questions on the overall strategy? Yes?
Yes, I think the stochastic programming people consider that this is an exact stochastic formulation, which I think personally is debatable. But so what's your view on this? Is that still considered an exact way? Is that neural net is an approximation?
No, this is a heuristic. Yes. So if the neural net is perfectly accurate, it's exact, but that will rarely be the case. But it can give you a heuristic solution as long as you're satisfying the constraints.
But on the left side, I mean, the original method would still be considered exact with 3 scenarios, right? Like the number of scenarios, it's exact under a fixed number of scenarios. That's a parameter, right? So if you have only 3 scenarios, mathematical programmers say, yes, it is exact with 3 or 3,000 or 300,000. So then you train. I understand why it is. My point is like I think it brings an interesting perspective to the field because these people they assume that this is exact even though they have very limited number of scenarios.
Correct.
Right?
Correct.
And here you can have way more scenarios.
Correct.
Right? You're still, but you still consider. Like for example, if the MIP model can only digest 10, right?
Exactly right.
You take 10 millions to build your
exactly
stuff.
Right. Then, yes. So we will do exactly that. Yeah. So indeed, we can ingest a lot more scenarios. And then even if we're approximate as a function, we can be more accurate in the aggregate because we are considering more of the support of that distribution over which the expected cost is actually evaluated. Right?
So you would be better than something that's reputed to be optimal.
Yes, except, in fact, it turns out, and my colleague Merve Boudour, because she's a stochastic programming person, she knows this very well, that counter to common intuition, actually, oftentimes, small number of scenarios is generally okay. It's very hard to get yourself to optimize for small number of scenarios, then take 100 times more and find that the optimal solutions differ a lot. It rarely happens. So we haven't been able to validate that killer use case, at least experimentally, but conceptually, you're right. Yeah. Question?
The MIPify and solve, just to clarify the diagram, the bottom thing is what is going to be MIPified. The bottom right.
Correct. This thing is going to be implemented as a MIP. Yes. And as a result of this, again, because we only care about first stage decision, you get your first stage decisions. Again, this is your initial investment. This is which servers are going to be on. Right? Now, once you fix the first stage decision, a scenario presents itself, you solve the corresponding second stage problem, fixing that X. Right? And that's how you use two-stage stochastic programming. So we use it in the exact same way. So this is the general framework. Now, I'm going to show you kind of how you can actually realize it. The main part is you need to embed this mixed integer program representation of your ReLU neural network. This is actually very well known by now, well established. People have been doing this for the last 5-6 years. In Gurobi these days, you can pre-train a PyTorch ReLU neural network and go to the Gurobi neural network library and just import the pre-trained model. And it will spit out the linear inequalities and variables necessary to represent that as a function. Okay? So this is becoming kind of mainstream technology. We're not doing anything new with that. But this is actually how our final optimization problem, this object, looks like. So you have your first stage objective. This is the same. And then you have your second stage objective approximation, sum over k scenarios. This is the probability of a scenario. Let's assume it's a uniform probability distribution. And then beta k is your prediction for the expected second stage cost for that scenario and a given x. And the way this beta k is implemented, this is just the output of the ReLU neural net, which is implemented through a bunch of, again, common set of linear equalities and inequalities. Yes?
I know you're saying this formulation is now kind of mainstream, but is it really that fast to solve?
It depends on a bunch of things. So if you have bounded inputs, you can do bound propagation, interval propagation. Then you can bound essentially the input to every neural network node unit and its output, okay? And that tightens the formulation. But eventually, you have to either implement it as a quadratic or as a big M type formulation. And if the network is huge, you will suffer, okay? But fortunately, here, we've not needed many huge networks. I'll talk about that. Yeah, but the formulation itself is mainstream, and there's a very active area of research on how you speed up MIP solvers to solve exactly this problem. Okay, and we haven't really leveraged the state of the art. Here, we're just using vanilla MIP solver. Okay?
Okay, but essentially, once the neural network is big enough, and if like your original optimization task you want to kind of approximate, this method would, it doesn't really make sense at some point.
Very good. So you've anticipated the exact next step. Okay? If you have a very large number of scenarios k that you're using to approximate this expectation, you need to embed this neural net k times to be able to get k predictions for one per scenario, right? So if you see this index set in the constraints, each of these constraints is multiplied, appears k times. It's one neural net being applied to k scenarios, okay? So then your number of constraints and variables grows. I mean, it grows linearly, but if k is 10,000, it might be a handicap, right? And now your approximate problem might be of size comparable to the original SAA extensive form, which is the exact formulation of the problem. And that's no good, right? So what we're going to do is we're going to get rid of this index set, okay? Instead of having to get one prediction per scenario, we're going to learn an additional neural network that summarizes any set of k scenarios into one meta scenario. And then we're going to predict only for that one meta scenario. Okay? It's one scenario that summarizes all the other scenarios. So I'll tell you what that means. This is kind of the key neural network trick. This is where neural nets are really, the fact that you can train these things end to end is extremely crucial and helpful. So we're going to change the supervised learning formulation. Instead of learning a function that approximates the second stage cost for one first decision, set of one first decision solution and one scenario, psi k, we're going to learn the value function for a set of scenarios. Okay? And then we're not going to approximate, for one, we're going to approximate for the sum, and this changes the structure of our data set. Now, in your input, you have not only a first stage solution and a vector representing the scenario, you have a set of such vectors. Okay? And if we can do this, then in this neural network mixed integer program, we have to only represent one forward pass in this neural net, not capital K of them. Okay? So how are we going to achieve that? We're going to do it by a simple observation, okay? The observation is that at test time, an instance comes in. The instance is represented by the base two-stage stochastic program and a set of scenarios. I know the set of scenarios in advance. So if I could pre-process them, aggregate them, combine them in some way into one scenario, I can just do that before I run this big MIP, okay? What's important is that this representation of the set of scenarios must be conducive to good predictions of the expected value function, okay? This is where end-to-end learning is going to come into play. What we're going to do is in the training phase, or even at test time, when you're presented with a set of scenarios, recall a set of scenarios is a vector representing, for example, which customers are available. Okay, think of it for stochastic server location. This is just a binary vector of size as many customers as you have. So I have two of them for the two scenarios. That's my scenario set. It's a set. There's no natural ordering amongst the scenarios. So that's important. The architecture needs to be cognizant of that. Each of these vectors is going to go through the same scenario embedding network. This is just a shared network, okay? Not one network with different parameters per scenario, one network that processes each of them in parallel, okay? The same network. And as a result, the scenario embedding network produces some nonlinear embedding that represents each scenario, okay? So one-to-one mapping so far. Then we're going to aggregate these embeddings by, say, averaging these vectors of arbitrary dimension, okay? So you've seen this already in Petar's talk, and I recommend you see the GNN tutorial, which builds up to graph neural networks starting with, sets, basically. This is an important thing, like understanding how to represent sets so that you get permutation invariance and equivariance. This is something that we leverage here. So basically, when you sum up a bunch of vectors, it doesn't matter in which order they were processed in the previous step, okay? So now, as a result, you get one vector of some predetermined dimension. That's a fixed hyperparameter, 128, 512, I don't know, that represents all your scenarios. Now, that thing goes into more nonlinear functions. Doesn't really matter in deep learning. We just like to do a lot of that. And as a result, you have some final embedding, which represents all case scenarios. Now, you put that with the first stage decision, exact same way as before, and you run it into your final ReLU network, which produces the expected second stage cost for the set of scenarios, okay? This is the only thing you need to embed in the final MIP, in the surrogate MIP. You don't need to embed any of these neural networks. These, you can think of them as preprocessors. You give me the set of scenarios, I run them through this, I spit out a fixed vector that represents that set of scenarios. And then I only need to optimize the first stage decisions over this network. Yes?
So before the first stage decision, they were based, like for one scenario, you could solve a deterministic problem and get the first stage. But what do you use now to optimize the first stage decision?
You're thinking about the labeling? Yeah. So earlier is just you run for a fixed X and a scenario, you run the second stage solver. Here you do exactly the same, but then you average the resulting values, because we're trying to predict the average value, not the per scenario value.
But you average the resulting first stage decision?
No, the first stage decision is the same. It's one first stage decision. That's why it's not here. It doesn't come into how you aggregate the scenarios, right? So this part is just producing some representation of a set of case scenarios, right? Now, why does this make sense? Because when we train this overall architectures, all these blocks, we train them end to end. So this is just mean squared error of expected second stage cost to your prediction. So you backpropagate through all of these, and you learn a way to summarize case scenarios into one good vector, such that when you combine that with a first stage decision, you get an accurate prediction of the value function. Okay? Yes?
So that final embedding is your meta scenario that
Yes.
you're talking about. So how important is it for that final embedding to be an accurate representation of the scenarios that you have?
So this is actually, some people have thought about this. Does there exist some vector which can be seen as an accurate representation of a bunch of scenarios? I don't think we have a complete or even basic answer theoretically. We know that
there is a counterexample that is not that.
There's a counterexample that there may not exist such a thing, that I think was constructed in an attempt to actually prove that you could do it. And so here the view is that of end-to-end learning, that if there exists a meta scenario that is conducive to accurate regression, then we hope that through gradient descent on a large enough data set, we can recover such a representation. Okay. Other questions? Okay. So now the pipeline changes very slightly. Now, your input is a first stage decision and a scenario set. You get an expected second stage cost. And in the embedding, you don't need to sum up the neural net outputs over k scenarios. The neural net just takes the meta scenario produced by this preprocessor here, and you optimize over this one network. Okay? So 1 instead of capital K. This matters a lot when capital K is 10,000, right? But overall, the architecture is the same. Okay. So why is this interesting? This is interesting because everything I've described applies extremely generically, essentially for any two-stage stochastic program. You only need the MIP labeler. You need to be able to solve the second stage problem for a fixed first stage decision and scenario. If you can do that, it's game on. You can even have second stage problems which are black box simulations. Like let's say your second stage problem is optimization over a discrete event simulations of hospital operations. We're actually working on a benchmark of that sort from the literature. So you commit some staffing decisions, and then there's some uncertain realization of demand to the hospital, and you're trying to optimize some other operations in the second stage, but actually the behavior of the system is best represented by a discrete event simulation. There's no analytical form that describes the system. This works fine with it. As long as you can solve for that, you're good, okay? And indeed, the benchmarks that we look at here for computational evaluation.
Elias,
yes.
Sorry. If you do discrete event simulation, if you go back to the slide before there, so instead of having a scenario set, there will still be a scenario set.
Correct.
You still needed to do this, producing a MIP, right? At the end.
That's fine. The only thing that changes is you need to solve the second stage problem. So you need to be able to optimize over a discrete event simulation. So if you have a simulation optimization method that can do that, so you give it the first stage and you give it the scenario, and it does some form of simulation optimization to try to produce the second stage solution, right? Or you have some approximation of it, right? So for example, there might be an LP approximation of the simulation of some sort. Then you can use that to label your data. And that's all we need. Everything else is exactly the same.
In the sense that there is a MIP.
Yeah, if it's still a ReLU network, no problem. As long as you can approximate the dynamics basically and get the value function with a MILP representable function, can be a neural net, can be a random forest, can be anything, then you're fine. Yes?
So normally the scenario set is okay, right? So you can play around with that, but how many first stage decisions you need to train this, right? So normally.
Yeah, so I'll show you empirically something to that effect. Yeah, but that's a very good question. Other questions? Okay, so you can apply this methodology to a wide range of problems. What we've looked at is I think more than what is typically done in computation, extensive evaluation of computational stochastic programming. So we have, I would say, 2 relatively classical problems. So capacitated facility location, you commit to facilities, and then there's uncertain demand, okay, that materializes at customers, and you need to assign customers to facilities. Stochastic server location I've talked about. You can think of it as a special case of facility location, but not really in this form. It actually has some other constraints that you can add. Both of these have binary first stage and second stage variables and linear constraints and objective. There's an investment problem from the stochastic programming literature, which actually has first stage continuous variables, pure continuous. Most stochastic programming doesn't work if you have even mixed integer in the first stage. Having continuous variables is a huge pain because these algorithms usually need some kind of enumeration over some finite set. And if you have continuous variables, you're out of the game. So this investment problem, what it does is you have some continuous first stage decision to invest in a project. And then in the second stage, you observe your uncertain budget. And then you need to decide what of the budget, how do you allocate the remaining budget? It's a binary decision, okay? And interestingly, the last problem we look at is from chemical engineering. It's a very famous pooling problem. So this is one of the canonical mixed integer nonlinear programming problems. So you have a network which essentially represents the production of a certain product through the combination of certain chemicals. It's nonlinear because you multiply quantities of chemicals together. So it has quadratic constraints. So nonlinear second stage problem. And the problem is you have to decide on the topology of your graph, input to output, materials to product, and then you will observe stuff about the demand or the quality of some of the materials, and then you need to see which edges in that will be active for your production, okay? So this problem is binary first stage, continuous second stage, because you can mix different materials in a continuous fractional way, and then nonlinear constraints, nonlinear objective function, okay? So there isn't one method that can accommodate all these different cases simultaneously because methods need to exploit a specific structure. Here, of course, we have a heuristic. We're not claiming this exact representation, but can very easily accommodate all of these things. Just one piece of code, basically. There's no specialization whatsoever. And we are working on some more applications where, in fact, we don't have an analytical form for the second stage problem, and it's a discrete event simulation of sorts, okay? So widely general. Now, how do we train it? Okay, we do the usual hyperparameter tuning. The neural nets that we use, like these different neural network blocks here, they're not very complicated. They're 1 to 3 layers, MLPs, 10 to 100 neurons, nothing crazy. We've done hyperparameter tuning. Doesn't really matter too much. It's not that sensitive. Amount of data, we found that we haven't needed more than 5,000 first stage decision scenario set pairs. So this plot is showing amount of training data versus mean absolute error, okay? And you can see clearly diminishing returns. As soon as you get 5,000 points, you don't really gain too much from going to 20,000 points. Here, the scale of the error is something like roughly 2% absolute error, relative absolute error, okay? So here, the scale is like 240, and I think the actual Q function is like 27,000 or something like that. So we're on the order of 1 to 3%. So you can actually approximate these functions relatively well for all the problems that we looked at. Okay? Yes?
Did you investigate the trade-off like X versus scenarios? Like if you have more first stage versus less scenarios or less first stage versus more scenarios?
Not in the training, but actually the problems will span these. So you'll see that the speedups that we get depend on that. And the other thing I wanted to mention is that training time is roughly data collection plus running stochastic gradient descent to train the neural net, often less than 3 hours for all the cases we looked at. I mean, it's nothing really that crazy. So all the data collection is CPU-based. The training is just standard, PyTorch neural net, okay? Now what I'm going to show you is speedups over 2 methods, the extensive form and the integer L-shaped method. And the graphs, for simplicity, I'm just going to focus on running time. So what you're seeing on the vertical axis is speed up relative to a certain method. So this is our method, embedding this trained neural network and optimizing, getting a first stage vector, compared to, say, the extensive form. Okay? These instances are interesting. These are the instances of the SIPLib library, the Stochastic Integer Programming Library, Stochastic Server Location Benchmark. So this is a benchmark that was introduced in the Million Variable March for Stochastic Combinatorial Optimization in 2005. This is a common benchmark for stochastic programming. If you're doing stochastic integer programming, you probably need to assess on these instances. And they are interesting because they're not instances that we generate. We're not generating random scenarios. It's fixed. So anybody can compare to our method and say, oh, we reach a solution that's slightly better or slightly worse. Okay? And essentially, in all these cases, we recover a near optimal solution, something like within 1% or 0.5%, et cetera. So I'm not going to worry about the optimality gap. It's all in the paper. It's essentially near optimal. What I'm going to focus on is the running time of this heuristic. So compared to the exact extensive form method, this is on the order of 10 to the power 4, so 10,000 times faster. Okay? For instances that have, in this case, 10 servers and 50 clients. These are the blue instances. And you get less speedups if your number of first stage variables is smaller. So the bigger speedups you get are when you have many scenarios and larger first stage problem compared to extensive form, because clearly extensive form blows up in running time. Now, interestingly, compared to the state-of-the-art method for this class of problems, the integer L-shaped, even compared to this method, which has been like very finely tuned, it's a very powerful method, it's much better than the extensive form. When the number of scenario grows, say up to 2,000, we also get a speed up of 100 to 1,000x. Okay? It's a very efficient method, and actually it's parallelizable. We run it with 80 cores. We don't run our method with as many cores. So we're giving it its best shot at converging very fast. Of course, it's an exact method. So in some cases, it can provide optimality guarantees, whereas we cannot. But in all cases, we essentially either recover an optimal solution or something very close to optimal. So we're not too worried about that. We're concerned more with finding good solutions very quickly. And these results carry over compared to extensive form in facility location, investment, pooling. You get orders of magnitude 1,000 to 10,000 times faster to essentially reach the best solution achievable by these methods. Yes?
So you are getting near-optimal first choice decisions, essentially?
Yes.
Okay. No. There was no, problem class that just it failed on?
No. In this case, it performed essentially well across the board. Some are harder, and you can see that in the paper, like the pooling problem, which is nonlinear, is a little bit trickier, and that's probably because the value function is a little bit harder to approximate. So some of the optimality gaps, instead of being below 1%, they're between 1 and 5% or something like that. But still, compared to extensive form, we do much better. So extensive form either needs too much time to find the good solution, whereas we find it instantly, or it doesn't really find anything at all, even after 3 hours. So we give it 3 hours. So all our methods run essentially in sub-second. So there's no result here that's more than 1 second total runtime. Yes?
So where do you get all the combinations, first stage and scenarios? Like in this one, 4 scenarios, but you must have trained on hundreds of scenarios plus different kinds of first stage variables.
Yeah, we train on roughly 5,000 pairs of first stage decision and scenario set. But actually, we train one model for say all these test cases, which have different number of test scenarios. We train only one model, and we sample also the size of the set of scenarios. So 4 scenarios, 10 scenarios, 20, kind of uniformly at random. So we train a model which knows to distinguish that this is an average over these 10 scenarios versus these other 100 scenarios. Train one model basically for each of the colors, and then we test it on all the different ones. Yeah. Okay. So in the interest of the nice weather, I'm going to conclude by saying that we've come up with this recipe for fast heuristic two-stage stochastic programming, where we learn an aggregate value function using a rectified linear unit deep neural net, and we embed that in a MIP using existing methods. And from that, we can get orders of magnitudes compared to existing methods. And we like this because it's quite generic and works very widely. And there are lots of interesting directions to go from here that I didn't have time to write. I do have some papers here in the space of specifically using learning to approximate certain parts of stochastic programs, but also recently similar approaches have been proposed for bi-level optimization, where you have a neural net that represents, say, the best response of an opponent in a bi-level game of sorts. So there are lots of ways to go from here, and one of them that we're interested in is which kind of neural net can represent which kind of value function based on the structure of the value function, because not every neural net can represent every function. And also if we can get any kind of guarantees in a kind of learning theoretic way. Like if I have more data, I get more accurate, how does that reflect in the optimality gap in some sense? So with that, I invite you to check out the code if you're interested in the method. Everything runs. If you have a few thousand CPU years to get rid of, you can just reproduce the paper very easily. Thank you.